All right. Hi, everyone, and welcome back. We are going to talk about, the acceleration due to gravity. So based on Newton's law of universal gravitation, we can also substitute our traditional force is equal to mass times acceleration into that equation and a couple other factors in order to determine our acceleration due to gravity on different planets. Okay, so this is how we can figure out information on Earth. Okay, so again, we took F12 is equal to G M1 M2 over R squared. And what we did is we set that equal to mass times acceleration due to gravity. Okay, now this mass would be the mass of the smaller object. Okay, so we'll call that M1. And so what we can do is from that cross out our M1, and then we are left with an equation that is very similar to this. Okay, now in this case, we have that this second mass is the mass of the Earth. Okay, and R would be the radius of the Earth. Okay, if we're looking for G for the Earth. Okay, so the acceleration due to gravity on Earth. Now, if we're looking at the acceleration due to gravity, say on Mars or on the moon or another planet, we can use this similar equation, but our acceleration due to gravity will be different. Okay, so pay attention to what we need to plug in here. So let's go ahead and do an example. So this is example 13.3. We want to know the mass of the Earth. Okay, so the values of G and the radius of Earth were measured with reasonable accuracy. Okay, so we use the standard values of G, R sub E, and the equation that I just pointed out to find the mass of the Earth. Okay, so let's go ahead and do this. So G, of course, is 9.8 meters per second squared. I'm just going to go ahead and round it off like that. R sub E, I went ahead and looked up because I don't have that memorized. The radius of Earth is 6.37 times 10 to the 6 meters. Okay. And again, we're trying to find the mass of Earth. So let's go back. We're going to go ahead and use this equation here. So we have G is equal to big G times mass of the Earth divided by the radius, and this is going to be radius of the Earth, in this case, squared. Okay, so the mass of the Earth is going to be equal to little g times R sub E squared over big G. I'm sorry, this pen is being really weird today. Okay, so then we can go ahead and plug in our values. So we have 9.8 meters per second squared times our radius of the Earth, which is 6.37 times 10 to the 6 meters. And we square that and divide it by G, which was 6.67, I believe, times 10 to the negative 11th Newton meters squared over kilograms squared. Let me double check that value there. Yes. Okay. So let me get out my calculator here. And so we have 9.8 times 6.37 times 10 to the 6, and that number is squared. Make sure I have all my parentheses in the right spot. And then we divide that by 6.67 times 10 to the negative 11th. And from that, we get the mass of the Earth to be 5.96 approximately times 10 to the 24th kilograms. Okay. All right. So that is our first part of the problem. Now going to the second part, it states estimate the value of G on the moon. Use the fact that moon has a radius of about 1,700 kilometers and assume it has the same average density as Earth. Okay, so let me go ahead and make some side notes up here. So density, remember, hopefully, I don't know if we have talked about it much, if any, but density is going to be the mass over velocity. I'm sorry, mass over volume, my bad, volume, not velocity, volume, okay? And for a sphere, okay, our mass is going to be the same, but our volume, we'll just do that. Our volume will be 4 pi over 3 times our radius cubed. Okay, so this is how you find the density of a sphere. Okay, and we're assuming that the moon and Earth are both spheres. Okay, so if we're saying that the Earth and the moon have the same density, we can say m of the Earth over 4 pi over 3 times the radius of the Earth cubed is going to be equal to the mass of the moon over 4 pi over 3 times the radius of the moon cubed. Okay, this is what we're saying. So notice that these two factors are the same, so we can go ahead and cross those out. Now we have this relation of the mass of Earth over the radius of Earth cubed is equal to the mass of the moon over the radius of the moon cubed. Or we can say that these ratios are going to be equal. Let's see. So the mass of the Earth over the mass of the moon is equal to the radius of the Earth cubed over the radius of the moon cubed. Okay. All right. So why did we care about that? Well, we don't know our mass of the moon, and we need that in order to solve this equation here. Okay. So now that we can find our mass of the moon, which we'll just have to flip these guys, we can determine G. Okay, so I'm going to go ahead and write it out. We have G is going to equal uppercase G times our mass of the moon. Okay, so the mass of the moon, if we flip this, will be, I'm going to go ahead and write it like this. Sorry, I'm thinking in my head. The mass of Earth times the radius of the moon cubed over the radius of the Earth cubed. Okay. And then we have divided by r, or the radius of the moon squared. Okay. All right. So then we have the radius of the moon squared can cross out with two of these guys. And so we can write this now as, right, okay, 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times the mass of the Earth, which we just solved for as 5.96 times 10 to the 24th kilograms. times the radius of Earth, which I don't have room to write, but we know it's the same as this one here. Oops. Okay. Or I'm sorry, it should be the radius of the moon, which is 1,700 kilometers. So let me fix that real quick. There it is. Okay. Radius of the moon. Which is going to be 1,700 times 10 to the third meters. Okay. And then divide that by the radius of the Earth cubed. So it's going to be 6.37 times 10 to the 6 meters cubed. Okay. So let me do this in my calculator quickly, as quick as I can. Let's see. Got this value times 6.67 times 10 to the negative 11th times our radius, which is going to be 1.7 times 10 to the 6th divided by radius of the Earth, 6.37 times 10 to the 6th, and that is going to be cubed. So G on the moon is then 2 point, oops, point, nope, dang it. 0.61, this is what happens when you run out of space, and this is in meters per second squared. Okay, so for all that math, we were able to determine the value of G on the moon. Okay, which is about, let's see, about third-ish. Yeah. Okay. All right, so let's go ahead and move on to the next problem. It asks, what is the value of G 400 kilometers above Earth's surface where the International Space Station is in orbit? Okay, so we want to find the value of G. Okay, so we know that G can be calculated in this manner, where R is going to be the radius of Earth, okay, plus whatever that distance is that we're looking for. So we've got G is equal to big G, the mass of the Earth, over R squared, right? Okay. And R is going to equal the radius of Earth plus that 400 kilometers. Okay, so the radius of Earth, remember we found was going to be 6.37 times 10 to the 6 meters. And then we have 400 kilometers, which, remember, kilometers is 10 to the third meters. Okay. So let's go ahead and put that in. 6.37 times 10 to the 6th plus 400 times 10, whoops, to the third. So we have 6.77 times 10 to the 6 meters now. Okay, so this is going to be our radius now. So G is going to equal 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times the mass of the Earth, which we found to be 5.96 times 10 to the 24th kilograms over R, which is 6.77 times 10 to the 6th meters, and this is squared. So now we'll need to put this into our calculator. So we have 6.67 times 10 to the negative 11th times 5.96 times 10 to the 24th divided by that value squared, and we get G above Earth's surface is going to be equal to 8.67 meters per second squared. Okay, now compare that to G on the surface of the Earth is about 9.81 meters per second squared. Okay, so as we get further away, that acceleration due to gravity will become less and less, which makes sense because that force will become less. Okay. All right, so I'm gonna go ahead and pause here, but I did want to make a correction. So if I go back here, I did make one mistake when calculating the velocity. Okay, so here, this is all correct, except for this displacement here. So let me go ahead and get out a different pin color, get out red. So this here is going to be, it's correct that the total distance of the motion between the two would be 6 meters, but we are just looking at one object at a time. So this for one object or vehicle should equal 3 meters. Okay, so this shouldn't be 6, it should be 3. And so that'll change this value, which will change this value, okay? And this one. So just watch out for that. I was just thinking this total distance, but we are just looking at one side, okay? Or one of the vehicles, okay? That's all I wanted to point out. And I will continue on with gravity in our next slides or our next video.